We are very happy to welcome Andreas Geiger, professor at the University of Tübingen and Max Planck Institute today. He's leading the Autonomous Vision Group. He has great works on 3D direction, motion estimation, generative modeling, and many others. You must know the Kitty benchmark, OCNet, and more recently the occupancy networks. Today he will talk us about his very influential work on 3D shape representations. Unfortunately, we had to turn this event into virtual, but we thank Andreas for agreeing to present remotely. We can turn off our cameras, I see most people already did, and microphones as well. The talk will be recorded and be put online after cutting the discussions. Andreas, maybe you want to say a few words about when to take questions.
Yeah, I'm happy to have questions during the talk if they occur or afterwards. Both is fine for me. Please just interrupt me, please, whenever you have any questions.
Great, thank you.
Yeah, thanks for the introduction, Gil, and welcome everyone to my virtual presentation. As I said, yes, please ask as soon as you have a question. Also during the talk, very happy to stop. Yeah, so in this talk, I'd like to share with you some of our recent research on implicit 3D models, neural implicit 3D models that can be used for 3D reconstruction and many other things, and that I'm very excited about, and also many other people have now started working on. So this is our research group, plus some visitors and friends from picture from one of our latest retreats. And in general, our goal is to make intelligent systems more autonomous, robust, and safe, in particular from the perception side. So intelligent systems need to interact with a complicated 3D environment, and thus they need to, amongst others, gain a very detailed understanding of the 3D geometry surrounding them. Now, 3D reconstruction, as we all know, is a hard problem, still is, and has been worked on for a very long time. Here is an example from Larry Roberts, 1963. So how does a traditional 3D reconstruction pipeline look like? Well, typically you have a set of input images. You first extract the camera poses using bundle adjustment. You extract dense correspondences, for instance, in the form of 2.5D maps, and you fuse them together, or maybe you refine the outcoming mesh further. So this is all fine, but it requires many images of objects that are have a lot of texture in order to apply these local cues, these local matching cues. However, humans are able to recognize challenging 3D scenes from even a single 2D image. If I show you this image here, for instance, you can clearly tell me which object is in front of which object, or what would happen if the person would move forward. Would it collide with this object here or not? So the question, which is kind of a headline for this talk, is can we learn to infer 3D from a 2D image? And there's two components to it. The first is learning. So we want to learn from big data sets. We want to learn this highly ambiguous problem, which cannot be solved mathematically, at least in the case of a single image. And we want to do it from a single 2D image, right? So this is at least for most of the examples I will show you. I also have examples for 3D point clouds as input, but several of them have 2D images input. So this is the overall setup that we are considering here in the beginning. On the left, we see a single 2D image. There's a neural network that takes this image as input and produces a 3D representation of that image. Now, the question that comes up in this context is, well, how should we actually represent the 3D output? And there's multiple options. What is a good output representation? The first option is a voxel-based approach, a voxel-based output representation, which is the most natural way probably to extend pixels to the output space of 3D. Voxels are a discretization of a 3D space into a regular grid. They are easy to process with neural networks because they just require to extend 2D convolutions to 3D convolutions. However, they have a cubic memory increase and therefore are limited to relatively small resolutions, even if you use data adaptive space partitioning schemes like octrees. And also they lead to certain Manhattan world biases. If you look at this voxel representation here at the bottom right, you can see that the voxels are of course oriented. They are oriented based on the coordinate frame that you have chosen. Right? That's not necessarily something that you want to be inherent in your reconstruction. Another possible output representation are points. Points are a discretization of a surface into a 3D point set. The disadvantage of a point set as an output representation for neural networks is that they do not model connectivity or topology directly. And existing approaches are also typically limited in the number of points they can output, as in this example for the point set generating network. Also, it's more difficult to model local correlations like in convolutions, but typically these approaches take as input a global shape descriptor. And finally, another output representation that has been used over the last 2 years were meshes. Meshes are also a discretization as voxels and points, but here into vertices and faces. And existing approaches also just handle a limited number of such vertices or limited granularity. And they are either requiring a class-specific template that gets deformed. So if you have, for instance, a face model, then you can deform that into the specific face that you want to infer. Or they lead to self-intersecting reconstructions, like in this case here, the Atlas network is basically outputting a collection of patches, but there is no guarantee for water tightness. So you get reconstructions that look like this. So in the work that we have presented at CVPR last year, we asked, well, do we really need to have an explicit output representation? Why not just working with directly an implicit representation, which does not require any discretization, in contrast to the previous representations that I showed you? Implicit models allow to model arbitrary topology and resolution, have a low memory footprint, and are not restricted to a specific class. And in this case here, I'm talking about a neural implicit representation. It's not a grid-based implicit model like a signed distance field that is defined on a grid, but it's defined directly through a neural network. So how could this look like? So the key idea is to not represent the 3D shape explicitly, but instead consider the surface implicitly as the decision boundary of a nonlinear classifier. So here we have a nonlinear classifier f with some parameters theta that takes as input a 3D location, so a 3D point, and a condition that could be an image or a point cloud or something else, and outputs for that 3D point and that condition a occupancy probability. You can see this here on the right. There is this decision boundary here of that classifier f that separates the red points from the blue points. In this case, it's a linear decision boundary in 2D. Here on the bottom, you can see a nonlinear decision boundary, which gives rise to this bench shape that separates the red points, which are interior to this shape, from the blue points that are outside this shape. Okay? And the decision boundary is then the shape that we are after. I also want to mention that there is some concurrent work. There have been 2 papers published at the same conference last year that work with very similar representations. So how does the model look like in detail? Well, this is very simple, actually. It's all using existing neural network blocks. So what we have here on the top is an encoder. This is either a point encoder or an image encoder or a voxel encoder that produces, in this case, a global shape encoding, maybe a 128-dimensional vector of the input condition. And this shape encoding is then injected at multiple locations using conditional batch normalization into the layers of a neural network. And this neural network here, in this case, this is a plate notation. So we have 5 examples of 5 subsequent stages of this. These are 5 subsequent stages of such a ResNet block. It's a fully connected layers here of such a ResNet network that is replicated 5 times stacked together. And the input to this network is, well, this condition here, C, but also a set of points. So we input T points of 3 dimensions that are first expanded into this feature vector, then put through these 5 stages. And the outcome of is the occupancy probability for each of these T points. We can do this for T points in parallel to exploit the parallelism of the GPU. Right? So we don't need to do it for every point separately. We can do it for a whole batch of points, both during training and during inference. Okay, so that's a very, very simple, fully connected residual network architecture that's conditioned on this green shape encoding. How can we train this model? Well, because we just have to classify the points if they are inside or outside. It's a binary problem. We can use binary cross entropy loss. This is in blue here. So the loss basically compares the output of the network, this is f theta, at a particular point to the true value which we assume to be known. So it's fully supervised here. For every of these 3D points here, we assume we have the ground truth label, which is that 3D point inside or is that outside of the surface? We obtain these points by making the models, for instance, the ShapeNet models watertight, and then randomly sampling 3D points inside and outside this model. So in this case, we use 2048 points that we use for a single object during one iteration. But of course, when we revisit that same object during training in another episode, we basically use another set of 2048 points for that object. So we dynamically sample these points. Okay. So this is a binary cross entropy loss. What we can also do is we can extend this is a purely discriminative model so far, but we can extend it to a generative version, which you call a variational occupancy encoder. It's basically a VAE that, in addition to this reconstruction loss here, has also an encoder Q that predicts from 3D points, 3D point set, a latent code that tries to approximate this posterior. And where we have the Kullback-Leibler loss that compares this distribution to a standard Gaussian distribution on the latent space. So we can basically also build a generative model with this representation. Okay, now one problem that we have is that because the output representation is implicit, we don't directly get a mesh representation that we desire out of this model. So we need to extract that mesh after we have trained the model, right? And at inference time. Now, doing this for every possible location in 3D space is intractable. What we do is we use a multi-resolution isosurface extraction technique that's very simple and incrementally builds up an octree by querying the occupancy network. So we have a trained occupancy network now, and what we do is we first place a regular grid over the 3D domain that we want to query. We query that network at all of these blue points here. This is the true shape here, or the shape that is encoded in this network. If the query point is blue, this means the network gives us as an answer that the point is outside of the object. If it's red, it's inside. So we know that this point is inside and the others are outside after these queries. Then we take all the adjacent voxels that are adjacent to the, or that are between an inside and an outside point, and we further subdivide those. We query those points iteratively, evaluate the points again, and so on, n times until we reach the final resolution that we want to reach. And then we can simply apply the margin cubes algorithm to extract the surface from this inside-outside points. Takes about 1 to 3 seconds in total. What we can also do is we can refine that mesh further by optimizing the occupancy function along the gradients of the occupancy field. And this can be simply implemented using double backpropagation, because with that we can get the direction in which we need to traverse the 3D space. However, in practice, it often turned out that like just going finer with this technique is sufficient for getting a good mesh. Okay, so the first experiment we've done with this model is to look at its representation power. So here on the left you can see a chair encoded at 3 different resolutions, and on the right you can see our model overfit to that same chair, the ground truth of that same chair. And what you can see is that, of course, at no matter what voxel resolution we have these discretization artifacts here, while our representation, our implicit representation, leads to very smooth, sometimes even a bit overly smooth results, and handles arbitrary topology, because topology is implicit, so it's extracted during the mesh extraction step. Okay. This is also visible from this plot here. What we have here is basically intersection over union on the left and parameters in the model on the right, and on the x-axis the resolution. And we have the occupancy network here in orange. This has basically a constant IOU and a constant number of parameters. And if we now increase the voxel resolution, we see that very quickly, in order to approach the same IOU, the same accuracy that our model has, we need to increase the number of voxels tremendously compared to the small number of parameters that we have in our model. In this case, this is a model that has been trained on 1,000 different objects. And so we can, in other words, we can represent in this simple neural network with just few parameters, we can represent very complex shapes. So here are some results of this model comparing it to baselines. I want to show you this in the form of a video. So here what you can see on the left is the input. This is the 2D image from which we infer a 3D shape, and we have re-implementations of a number of different baselines that use different output representations. Here is the work from Joy et al., which uses voxels. This is the point set generating network that uses points. This is a mesh-based representation. And this is the output after the hierarchical surface reconstruction of our technique compared to the ground truth on the left. The same also works for point clouds. So here in this case, the goal is from a point cloud encoding to reconstruct the shape. So here we have a point cloud to point cloud result. This is point cloud to a mesh result. And this is our implicit representation that we infer compared to the ground truth. We can also tackle voxel super resolution as a task. So here on the left, we have the input in form of a very coarse voxel grid, and we train a network to predict a fine 3D shape. You can see that we can recover some of the details that are not really present in the input. And here are some results for our generative model. What we've done here is we have trained a generative model for multiple categories. So this is not only for a single category, but for multiple. And then we traverse in the latent space. So we generate novel shapes that are not part of the training set here. Okay. So if there's no questions, I will proceed. The next question we ask is, can we also learn about the object appearance? What you've seen so far was only about the 3D shape. Can we also learn something about texture, for instance, right? And of course, we can use a very similar model to infer texture. So what we've done here is we take as input already a 3D geometry. This geometry could be either the geometry of a CAD model, or it could be an inference result from the previous model that you've seen. And we take a 2D image of that object as an input. And then we use what we call a texture field that queries any point on the surface of that 3D model, queries for that point the texture. So we predict an RGB value for each point on the surface of this object in order to yield a texture 3D model. So here's the overview of this approach. We again have an image that's encoded using an image encoder, a 2D neural network, into a latent code C, or condition C. Then we have the 3D shape. From the 3D shape, we sample a point cloud, encode this using a PointRend into a shape encoding, that is S. And then we can, for every point on that 3D object, so for instance, we can render this into a depth map, and then we can unproject the 3D points. We can basically query each of these 3D points here, conditioned on C and S, using this texture field to render a color for that 3D point. And we can compare that color using a standard L1 reconstruction loss to the true color of that pixel in the ground truth. It's supervised training here. Right, so this is how we train this model. We can also apply this model in a generative fashion. So here we don't have this image encoder, but we have a GAN model where we have just a normal distribution on the latent code, and we have an adversarial loss that compares the predicted and the unpaired ground truth image. And what we can also do is we can use a variational autoencoder version of this model where we don't have an adversarial loss, but we have a VAE encoder that re-encodes basically this image into latent code, and we have again the reconstruction loss here. So here's again a similar experiment as I've shown you before. This is to demonstrate the representation power. On the left, you can see the ground truth cat, ground truth person here. Then you can see what happens when we overfit to this representation, what we obtain, and the voxel-based representation, color representation here on the right for comparison. These are some more examples. You can see for textures, it doesn't work quite as nicely as for geometry, because texture is often very high frequency. You can see that some of these high frequency details are lost here. However, there's some ideas which I'll present to you later that can overcome this problem. So I want to show you some results now. Let's look at this video instead of these images. So this is a single image text reconstruction. On the left, we have the input image and the ground truth shape that was basically texturized using our approach. We compare this to a simple novel view synthesis baseline that leads to very noisy results because it just has a single input image here on the left. While our representation is, of course, consistent when you rotate the object because it's not in an image-based representation. Okay. Yeah, I have to say that, of course, you could. This is a very simple novel view synthesis baseline. You could do better than this. This is a very simple image-to-image translation baseline that we show here. This is rather to show that the 3D, the benefits of doing it in 3D. So this was what you've seen before, was based on renderings of 3D ShapeNet models. Now we can also take a CAD model and superimpose the texture of a real object from a photograph. This is actually not exactly the same car type. Still, it is able to transfer the texture reasonably well. And so here we have now the combination of the two approaches. We have the input image here on the left. Then from this input image, we retrieve the reconstruction using the occupancy network and then texture it using this texture field. And here are some generative modeling results. Here are some latent space interpolations. You can see how the color of the car changes, yet the windows always stay kind of grayish or blackish. But what you can also see is that the model leads to very smooth results, overly smooth results. Okay, so another thing we looked into is what about object motion? All right, so far everything was static. We had geometry, we had texture, but what if we want to infer objects in motion? It turns out if you directly extend this idea of occupancy networks to 4D space, this is really hard because of the curse of dimensionality. Going from 3-dimensional output to 4-dimensional output is not easy. And so we've used a different model in this case here. What we do instead is we represent the shape still only in 3D space using a 3D occupancy network that is evaluated at a particular time step, let's say at time step t = 0. And in addition, we represent motion by a temporally and spatially continuous vector field. The advantage of this is that this is really very smooth in comparison to representing each time step, at each time step, the full 3D shape. We can represent this this very smooth motion field that is illustrated here on top much more easily with a neural network. And the relationship between a 3D trajectory S and the velocity is of course given by this very simple equation here. It's basically just the velocity is the derivative of the trajectory with respect to time, right? And we can then establish such trajectories from the velocity field and from the shape representation by solving for this ordinary differential equation. And it has recently been shown also in one of NIP's best paper awards that this is actually a differentiable operation using older techniques. We can obtain gradients for this, and so we can train the entire model end to end. In this case, the input is not just at a single time instance, but we have multiple time instances. Could be the first frame and the last frame of a sequence. The model automatically establishes correspondences in this case. It could be images or it could be point clouds. So we have this multi-point and multi-image encoder that again gives us, in this case, a global shape and motion representation that are then the input to our model here, X. The model then predicts a velocity vector field and an occupancy at time 0. And then we can solve for this ordinary differential equation in order to evaluate the reconstruction loss, right? So we can take the ground truth at a particular point in time. We can then warp that ground truth through this trajectory that is implicit through this ordinary differential equation to get actually the location at time step 0, and then basically evaluate the inside and outside function. Here you can see also the deformation in the background that this vector field induces on the shape. Okay. And this works much better than directly extending the occupancy network idea to 4D, as I will show you in a second. We can evaluate, we can learn this model using the standard reconstruction loss, but if we have correspondences available, we can also use a correspondence loss. However, often we are just given unstructured point clouds as input, so we can directly use this model only with the reconstruction loss. This is the neat feat about this model. Correspondences are optional, and they are, if they are not given, implicitly established by our model. Right. So let me show you some results here. Again, a video. So these are point cloud completion results. In this case, the input is a point cloud, is a sequence of point clouds over time. And here you can see what happens if we use the idea of the occupancy network and directly extend 3D to 4D. You can see that the model is not, the representation power of the model is not sufficient to capture the arms properly. This is the result of a point set generation network, and this is the result of the occupancy flow network. What you can also see here in color coded is the correspondence map. So every point that is basically a certain color corresponds to a point in another frame of the same color. There's another example here. And here are some results on reconstruction from image sequence. So we have on the left an image sequence as an input, and on the right, the reconstruction of various baselines and our occupancy flow model just based on this image sequence. We can use our model for interpolation also. So here in the case, we take a high resolution model that's available at certain discrete time steps. And because we have now established correspondences, we can just propagate all the vertices through our vector field by solving this differential equation and obtain a smooth trajectory. Okay. So moving forward, we wanted to answer the question, well, all of these models that we've seen so far require full supervision, right? So we require full supervision. We always need to know the occupancies, the ground truth occupancy for these points. Are they inside or outside at every frame and at every location in 3D space? So can we actually learn these implicit models not directly from images? There has been great success in learning representations, deep neural network 3D representations from images. for instance, mesh-based representations or voxel-based representations. So can we build such a differentiable renderer also for these implicit models? The architecture we use here is simpler than the one that we had before, where we need to subsequently combine an occupancy network and a texture representation. In this case, we have just one network that does both for us. So we have, and this is also an advantage of training this model not in the supervised fashion, but directly from images. So we have an image encoder. This is the input condition. We have an input encoder G that generates this latent code C. And we have a query point P, or a set of query points P, that are the input to this network. Again, we have 5 ResNet blocks. We have actually figured out that it's much easier and not necessary to do this conditional batch normalization, but we can just directly concatenate or sum up the latent code here with the feature representation, and this yields at a much faster runtime, almost the same results as conditional batch normalization. So we've changed the model here, but otherwise it's almost the same. But here, in this case, the output is 2 heads. So we have 1 head for every point predicting the occupancy probability, and another head that predicts the texture value, the color value at that point. Okay. So we don't predict color only at the surface, but we basically directly predict the occupancy and the color everywhere in 3D space. Now, how can we apply a neural network here? How can we train the neural network here? For training, we need to, of course, apply the forward and the backward pass. The forward pass corresponds to the rendering operation. So how can we render such an implicit representation? Well, what is illustrated here is such an occupancy network representation in 3D space and an image plane. What we can do is, for all pixels on that image plane, we can go along the ray that corresponds to the pixel, traverse 3D space via ray marching and route finding to find the intersection of basically where the surface is equal to tau, like this decision boundary here. We can then evaluate the texture field. So this was for the geometry. Now we can evaluate the texture field T at that point location P hat, at that inferred point location P hat, and we can insert that color at the corresponding pixel location. Right? So we can transfer this red color here, and we can do this for all the other colors as well. So we get the image using this technique. Now, how can we actually implement the backward pass? For the backward pass, what we want to do is we want to compare the prediction. This is what the model gives us based on the current parameters to an actual observation here. You can see that the observation and the prediction are slightly different. So this one is a little bit more red. So we use a standard reconstruction loss for this. We compare the intensities at every pixel, for instance, using an L1 loss. So what we need to do now in order to implement the backward pass and to backpropagate the gradients is, of course, to establish the gradients of this loss function with respect to the parameters of the network. Now we can apply the standard chain rule here, and this leads to this expression here. And the derivative of the inferred image, this is the predicted image I had here, with respect to the parameters is just this total derivative, because both the texture and the location depends on the parameters. Now the question is only, this is all easy, but the question is, how can we actually compute the derivative of this 3D location with respect to the parameters? And what we show in this CVPR 2020 paper upcoming is that if we project this gradient onto the ray, we obtain a one-dimensional quantity, and therefore it's invertible. And therefore this gradient here, this gradient of the 3D location with respect to the parameters has actually a closed form solution that looks like this. Okay, I'm not going to go more into details here, but we have a very simple closed form solution for this expression here, and therefore can compute in an analytic fashion the gradients of this loss function. So this is nice. So this basically completes our differentiable renderer. And what we do here, basically, you can see all the terms here that depend on the parameters theta. Now based on the observation, we update the parameters theta, and you can see that maybe in this case, in this simple toy example, the the texture representation updates like this, and the 3D representation updates like this. Okay. So the key findings of our CVPR 2020 papers is that implicit models are actually differentiable. There is an analytic solution even to the gradients. And one nice advantage over differentiable rendering techniques, for instance, for voxels, is that in this case, there is no need for storing intermediate results. If you have a voxel-based differentiable renderer, you need to store intermediate results while traversing the ray. In this case here, it's actually not necessary. So it's very memory efficient. It allows for training implicit models from RGB or depth. And as we've shown in the paper, it's possible to train models by having just a single observation per object. You have many observations, of course, of different objects of the same category, but a single observation per object is sufficient to establish enough gradients for backpropagation. Okay, so here are some results. Let me again show you this video. So what we have here on the left is an input. We have a baseline, soft rasterizer, pixel to mesh. This one here uses 3D supervision. And this is the result of our technique using either pure 2D supervision or 2.5D supervision. So you can also use this differentiable rendering technique if you have depth maps accessible. So then, of course, you can get better supervision than just looking at the raw image, which in this case is even not very textured. So it's a very challenging task, actually. Okay, so here's another example. It's an airplane. See the soft rasterizer output with 2D supervision, pixel to mesh approach with 3D supervision, and our approach with 2D supervision and with 2.5D supervision. So all of these results that you can see here are single image 3D reconstruction results, just the supervision used for training is different. What we also did is we applied our model to the DTU data set, which you can see here, to show that it actually works for real data as well. And you can see how our reconstructions look like. So we have the shape, the texture, and normals represented here. Okay, so these are overfitting results. So this is not conditional image-based reconstruction results, because we have not enough training data here for training this conditional model, but this is overfitting to this sequence to these scenes here to demonstrate the capabilities for 3D reconstruction of that representation. Okay, so now in the last few minutes, I want to show you, I'll give you a little overview over some very recent results. As I mentioned before, these implicit models are becoming en vogue and used in many different areas. So I want to show you a little bit what people have been doing. There are some results from our group, and there are some results from other research groups as well. So here's a very recent archive paper from the group from Lippmann et al. That basically also have a similar idea as we did with our differentiable renderer for implicit models. In this case, they model also the surface normal, which allows them to model material properties. So they can basically train these implicit models then using a very similar technique as we do, but using BRDF representations, which is quite nice, I think. I always give the, and if you're interested in this talk, I can give you the slides afterwards. I always put the citation to the papers at the bottom here. This is a recent work from us, a recent result from us, where we went beyond this texture fields model and tried to represent surface light fields. Surface light fields, in contrast to texture fields, are also depending on the viewing direction and the light setting. So what we have here is, the left part is very similar to the texture field approach. We have an image encoder that encodes an image into a latent code C, and we have a geometry encoder that encodes the input shape into a shape encoding S. And then we have an appearance field that predicts appearance properties, material properties, if you want, for every 3D point in space. And then we have a lighting model on top of that, that conditioned on the light setting and on the view direction predicts then the actual output. And this allows for conditioning this model also on the view and the light, in contrast to the texture fields approach. So you get material specific and light specific effects. So here are some results. So for instance, what we can model with this is also shadows. So we have a point light source here. On the right is the ground truth rendered using a sampling-based bidirectional path tracer. On the left, you can see our results that are trying to approximate what you can see here on the right. If I go back, you can see that the shadows are nicely captured, but there's some reflections that are not captured that well, which are also very difficult to capture. Here's an example for reflections. What we can then do is we can train this model using point light sources, approximate point light sources, but we can apply it using environment maps by considering every point on the environment map as a point light source. And when we can then basically render using this neural rendering technique, we can render results like this one here. So this is with a different environment map. We can see trees and clouds. Yes, and this is a prediction from a single view. We have a baseline here, a simple baseline image-to-image translation, which doesn't work so well, where you can see what happens when we change the light. In this case, is also conditioned on the light location and the viewpoint. You can see what happens. Now here, this is our results compared to the simple 2D approach. And you can see what happens if we change the viewpoint or change the light location. And this is all inferred again from a single image by training on a large corpora of such scenes. And this is a result which combines geometry inference using an occupancy network and the this conditional surface light field approach that I've just talked about. Yeah, and it also works for real input images. So here we have a real image as an input. We encode that image into a latent code, and you can see on the right-hand side then the result of the geometry and surface reconstruction. Yeah, and there's also some latent space interpolations possible. So you can also apply this technique as a generative model. Okay. Another problem that these implicit models have is the representation capacity. We've already seen that both geometry, but in particular also appearance, suffer from this very smooth function class that fully connected networks are able to represent. So this is the standard model that you can see here on the top, the standard occupancy network, where the input is a feature encoding, and this passed through multiple layers of fully connected ResNet, and the output is occupancy probability. Now, one way, one remedy to this problem, to go to larger scenes, so a scene like this one here, this is from Matterport 3D, would not be able, you wouldn't be able to reconstruct such a big scene with such a simple, fully connected network. It's simply not, the capacity is not sufficient. So one remedy for this is to combine this model with convolutional networks. And this is what we've worked on in the last few months. So here, one example how you can do this is you can have a 3D convolutional network that operates at a relatively small resolution. You encode features. In this case, the input is a 3D point cloud, a very sparse 3D point cloud. You encode these features into a 3D volume, and then you can query this volume using trilinear interpolation at any possible 3D location. So you get the features at that location, and you also get the location as an input to this fully connected head here, this occupancy head, and then predict the occupancy probability. And with this fully convolutional architecture, then you can go to much higher resolutions. Another very related work is PiFU, pixel-aligned implicit functions. You have probably seen this work before. what they do is basically they also have localized features as we have in the convolutional approach, but they do convolution in the image domain. So we try to do image-based reconstruction, then they take the features, they compute features in the image domain using an image encoder and query these features by back projecting the 3D location to the corresponding pixel in the feature map, right? And then this is the input to such an fully connected model that takes the features and the depth in this case and predicts inside and outside or the texture, and you get such nice avatars. There's a very recent extension to this model called PiFU HD, which gets even nicer reconstructions. One work I also like is a recent work by Funkhauser's team, where they combined, we are also working on this, they combined these implicit models with primitive-based representations. So here, each of these little ellipsoids that you see here is represented by an implicit function, and by combining these implicit functions and together, you get the full shape out, right? And of course, this has nice applications to modeling articulated human bodies, and you can see that the body shape is very well preserved using these local representations. In this case, each of these little occupancy networks here has a is a more shallow representation compared to our occupancy network that would be asked to reconstruct the entire shape. So you can use more shallow networks, and as a collection of these shallow networks, you get very nice shapes. Also, recent work on novel view synthesis using these implicit models is NeRF, representing scenes as neural radiance fields, where the idea is that instead of predicting just the occupancy, you try to do ray marching and integrate the transmittance along the ray. So you can also represent, for instance, translucent surfaces better, and you train these models only from images, okay? So they obtain this results here. I can show you some results in this video by, let's see, by training this model only from images. In this case, a lot of images from a single scene. So we basically overfit to a single scene and get them very nice novel view synthesis results. On the left, you can see some previous work. On the right, you can see the results of this neural representation that is trained. Takes about 10 to 12 hours to train this for one scene. Okay, and this one here, I also want to highlight a PointRend image segmentation as rendering. In this case, same idea, an implicit model, but in this case used for instance segmentation. On the left, you can see the result of mask RCNN for instance segmentation, and you can see how coarse that boundary is. And the reason for this is that the features that are used here are 28 by 28, so it's not possible with such coarse feature maps to represent the shape very precisely. Now, what this PointRend paper does is they basically do what occupancy networks do in 3D in the 2D domain. We iteratively at inference time discretize the 3D space based on where the surface is actually located. In this case, the surface is the silhouette, and get much finer details. For instance, if you compare the fingers here on the left side and on the right side, they get much finer details. They get each finger separated out using this implicit head on top of a similar to mask RCNN backbone. Yeah, so that's concluding my talk. Just the final slide here. Take-home messages. Neural implicit models are an effective output representation for shape, appearance, material, motion, and more. There's no discretization necessary. They can model arbitrary topology in 2D and 3D or 4D. They can be learned from images via differentiable rendering, and they have many applications in reconstruction, view synthesis, segmentation, but I suspect we will see a lot more in the future. However, Here are some of the downsides of these models, or some of the things to work on. Geometry must be extracted in a separate post-processing step. In the case of occupancy networks, this takes between 1 and 3 seconds. Extension to 4D or higher dimension in general is not straightforward because of the curse of dimensionality. The fully connected architecture and global conditioning lead to overly smooth results. But there is some promising ideas out there already. For instance, in NeRF, they use a explicit input encoding that is high dimensional compared to the simple 3D point as an input. And in our convolutional architecture or in PiFU, we use local features that also help here.